Hi. So today, right now, we are going to look at a function in Haskell, another function with some examples. I tried to pick interesting ones, so let's get into it. So the function today is cycle. Let's take a look at it, at the documentation. So what is it? So it ties a finite list into a circular one, or equivalently the infinite repetition of the original list. It is the identity on infinite list. So let's take a look at an example. So say it's an infinite list, so I need to do a take so that we can get like a finite list. So let's take 10 from, let's say, so 1 second. So first let's take a look at the type of cycle. So it takes a list and gives a list back. And so let's take 10 from cycle of, let's give 1, 2, and 3. So with that we get 1, 2, 3, and then cycle it again 1, 2, 3 until we get 10 numbers. It just stops when we get 10 numbers. Not necessarily after a cycle is over. So here you can see a cycle is truncated and we get only one of the cycle. So let's say we can do something similar. Take 7 cycle, say 1 until 4, and yeah, that same thing it gives us. So 1, 2, 3, 4. So that's the range 1 until 4, and it starts a new cycle, and it stops at 3 because we got already 7. So the first example I have here is Euler problem 35, circular primes. So let's take a look at that one. So Euler problem 35. So for example, the problem says that if you are given 197, it is called a circular prime because all rotations of the digit 197 are 197, 971, and 719, and all these numbers are themselves prime. So that's why 197 is a circular prime. And so all numbers below like 100, they are like listing the circular primes number under 100, and there are 13 of them. And the question is to find out how many circular primes are there below 1 million. So let's see that. So the way I implemented it here is I defined the circular where we get a number and it checks if it's circular. So by using this all function, so what does all do? So all it does is apply to a predicate and a list. All determines if all the elements of the list satisfy the predicate. For the result to be true, the list must be finite. Yeah, so basically that means that all here would check all numbers in nims, and it checks if each one of them is prime. And what I'm going to put in nims is basically all the permutations, all the rotations, if you will, for the number that I'm passing in here. So for example, for 197, nims will contain 197, 971, 719, and yeah, basically all the possible permutations. And so it would check if each one of them is prime, and that's the definition of a circularly prime. So let's calculate then all the permutations of the number. And so to do that, we are going to first need the size, like the number of digits in the number we get passed. And so to do that, we just show p. So we get the list, we get the number as a string, and we take the length of that string. With that, we get the number of digits. And then in order to compute like all the possible permutations, we use cycle here, which would be pretty useful. So the way we will do that is we will use a couple of functions: read, take, and drop. So let's go through these one by one. So what does take do? So take n applied to let's take for the list, applied to a list xs returns the prefix of xs of length n. So for example, take 5 from hello world, we take the 5 first characters, and those would be 1, 2, 3, 4, 5. So it would be hello. From this, the 3 first elements, 1, 2, and 3. And basically you get the idea. For drop, it's very similar. So if we take dot of a drop, it drops n xs, so returns the suffix of xs after the first n element are dropped. So for example, drop 6 from hello world, we drop the first 6 characters, so 1, 2, 3, 4, 5, 6. So we drop these characters, and we leave only the rest, which is word here. Same thing, drop the first 3, drop 3 here, we'll drop 1, 2, 3, and we'll print out, we'll leave only the rest, which is 4, 5, which is what we got here. And the type of drop, it just gets an int, the number by which to drop, and the list. Okay. And read is very similar. So read, the only thing that it does, it reads input from a string which must be completely consumed. So it just reads the whatever we have here. And so what we are doing here is we are taking from 0 to the length. So say if we have a prime like 197, the size would be 4. So the size would be 3. Sorry, the size would be 3. And so what we are going to do is we are going to go from 0 until 3, which is the size, and we are going to take. So we are going to take 3, which is take L here, and we are going to drop n, and n is like in this list. So n is 0, 1, 2, 3. And what we are going to do is, so we are mapping with a function that takes as a parameter n. So this map here gets first 0, and then 1, and then 2, and then 3. So, and then, sorry, 2, because the length is, L is 3, so that means L minus 1 is 2. So that means that our function here will be applied for 0, 1, 2, and that's it. So applying it to let's see if applying it just to 0. That means we are going to apply the function read, take L, which is 3, and then drop 0. This is the first iteration. And we are going to just apply this function here to cycle of PS, which in our case here it's 197. It's a string. And so we apply that function to this. Yeah, a second. Let me see. So if I do show 197, that would be that. If we do let PS equal to that, that would be this. And let's say L is length of PS, so L would be 3. And then let's see what would nyms contain. So if we say like let 1 second here. Yeah, so let's skip the read for now. So you can see here, by applying this function, we got 197, 971, 719, all the permutations. How did we get that? So every time, so first we take, let me take you through the first iteration. Like first take like the entire length, Let's get rid here of this, and we get the PS. So this is the first application, right? And so it gives us this. The second iteration is drop n, so n changes to become 1, and so we drop just the first one. And so since we are cycling here, this cycle means that we will get 197, and then, so let me do this. So if we do take like 10 of that cycle, like of the cycle of the number 197, or let's just go with like 8. So you can see we would get 197, 197, 197, and basically if we drop 0, we will get just 197. If we take like 3 and drop 0, we will get this 197. If we drop 1, we would get, and take 3, we would get 971. If we drop 2 and get like 3, we would get 719. So you can see that this way we get all the rotations or all the permutations of the number. And so that's how we are using cycle here. And so we put that in nyms as a list, and then we check that each one of them is prime. And basically that's all we need to do. And what happens after that is that the question is how many circular primes are there below 1 million. So what we do is we take all prime numbers below 1 million with this, which are the candidates to be circular prime, and we just filter by this function circular that checks if the number is circular, and we count them. And at the end, if we run this, it's going to take a little bit of time, but I ran it before and it returned 55, and here it will return the same thing. Yeah, so we can see it returns 55. That's the number of circular primes below 1 million. Now let's take a look here at our second example. So our second example here is to define a function called funky map, if you will, that takes as arguments two functions f and g and the list xs, and applies f to all elements at even positions like 0, 2, 4, 6 in some list, and j to all elements in odd positions like 1, 3, 5, 7 on the list. And so we are going to use cycle here. So we get past two functions f and g, and we do use zip with using this operate function here, and we cycle through f and j. So why does this work here? So cycle just given a list repeats it infinitely. So by doing cycle fg here, we just repeat it infinitely. So we get fj, 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 fj just infinitely. And this $sign here is just given a function and an argument. It just applies the function to the argument. That's all it does. And so what we are doing here is we are creating a list, an infinite list fj of fj, and we apply it to whatever list we get past it to funky maps. So that means f will be applied to the first element at index 0, j would be applied to element at index 1, f will be applied to the element at index 2, j would be applied at element at index 3, and f will be applied to element at index 4, then j applied for the element at index 5, and it will keep going like this. And with this way you can see that f will be applied to all even positions, and j will be applied to all odd positions, and this is what we want here, and that's basically gives us whatever we want, the result that we want. To apply this, let's just see how it works. So we can say funky map. Let's say we want the elements at odd position, we want to multiply them by 10, and the ones at odd positions we want to multiply them by 100. And let's give the list like 1, 2, 3, 4, 5, 6, 7. So we can see the first one 10, second one 100, first one 13, 100, and you get the idea. Now let's take a look at another example, third example here. So, and you can see here it was very handy using cycle with the two functions just to alternate between them. Now another example is if we want to double every second item in a list. So say we have this list 1, 2, 3, 4. We want to double every second item, so we want to double 2 and we want to double 4. Let's call it map second. Just a function that gets applied to, so we decompose the problem here. So we want to double every second item in a list. So let's just create a function that that maps on the second item of a list and then pass doubling to that function. And so map on the second element of a list, we would use the same pattern as we did here. So we want here we applied j on every second item on the list, on every second item on the list, because we are applying it to all add positions. So we apply it to 1, which is the second item because it's after 0, and the one after that at position 3, the second item. And so what we want is j to be our function f that we want to apply. And since for the element at index 0 and then at index 1, which is not the second item, it's the first item, for that one we don't want to apply anything, so we can just use id, which just gives the number as it is. Because if you look at the definition of id, it's just the identity function. It returns the value itself. So id of 4 is 4. And so for our list here 1, 2, 3, 4, if we apply id to 1, we would get 1, and then we would want to multiply by 2 for 2. And for 3 we want to apply nothing, so id. And so we use that pattern, and now we have our map second, and in order to double then every second item, we can just pass to map second our function doubling, which multiplies by 2. And if you take a look at the application of this double second, just take the application of it. Yeah, it doubles every second item. So 2 becomes 4, 4 becomes 8, and that's all there is. So now let's take a look at another example. So we say we want to print this pattern here, this string pattern, character pattern here, or ASCII pattern if you will. And what it consists of is that the first line is just dot, and the second line is dot plus, and then dot, dot plus, dot. So the first line is boring, just a list of dots. The second line is a succession of dot plus dot. And the third line is just a succession of plus dot plus. And the last line is just a succession of dots. So what we want here is a succession of dot, a succession of dot plus dot, and a succession of plus dot plus, and a succession of dot at the end. And so what we get passed is the number of occurrences of each of these characters that we want, and then the first character, which is that we are alternating here between two characters, and so we want first character, the second value, and then we get as a result a list of lists. And so let's say here the example here, it's 48 characters. So we need to get past the length and the first letter or the first value and then the second. And the way we use this, so the pattern itself is just taking the first element that we get past and constructing a row out of that. So that's a list of that element. So that's represented by A. And for the second, it's dot plus dot, which means it's, so in our case here, dot is A and the plus is B. So you can see that this pattern here is just A, B, A. And this pattern here is just, since plus is B, it's just B, A, B. And the pattern where we have just dots, that's just like A, multiple times, a repeated. Okay, so that means the first line is just a repeated, so we can just say it's a repeated. The second line is just a repeated, so a repeated. The third line is just b repeated, b, and the last line is just same thing, a repeated, so and in order to represent the fact that it's repeated continuously until we reach 48 numbers, we can just apply cycle. And in order to truncate to just get the 48 length we want, we just take 48 or whatever length we get past, and we map that function to this list of lists, which is the list of all of these. So first it's an infinite list, and we just truncate at 48 here. Okay, now that's all. Basically the pattern is just doing this pattern here to satisfy the form of this, and then we cycle so that it keeps continuing, and then we truncate by taking the length that we are past. And so applying that would be just pattern, and the length is 48, and a is dot and b is plus, and we just do unlines here just to concatenate them, where each one of them consists of a line, and we print them. If you take a look at a line here, the documentation of the lines, it's the inverse functions kind of lines. So it joins lines after appending a terminating a new line to each. So it joins this line after appending a terminating a new line for each one of them. And that's basically all. And so you can see the usage here of cycle is kind of the core of the solution here. Now that's all for cycle, and see you next. Bye bye.